Hello, everybody. I'm Jeff Gavornik. And, I looked at this and I realized as I walked in, I got a little bit nervous and I realized that there's the data science component. And although we do a lot of the things that people have been talking about, like dynamic system modeling and statistical modeling to understand the data we're recording, I didn't actually put any of that data in the talk. But then I realized I'm the last speaker and the title of this thing is neuroscience, data science, and back. So we can just do the and back part now, which is coming back and talking about neuroscience. So what I'm really interested in is how synaptic plasticity occurs. What are the sort of activity patterns that drive synaptic plasticity, and how that synaptic plasticity encodes temporal information into cortical circuits. So it's sort of a subset of the question of how does the brain represent time, but specifically what I'm interested in is how does the brain learn to represent time based on its experiences. And I do this in the mouse and the visual system. If you know anything about, if you've taken introductory neuroscience courses, you know that activity in the visual cortex represents spatial features that exist in the visual field when you're looking at things. But it turns out that that's only one sort of limited way of looking at what's happening in the visual system. And so this is data that was published before I came to BU, and it just shows that if you take a mouse and you put them in front of a screen and you show a spatial temporal sequence of images for multiple different days, the response when the mouse sees those images changes in a way that encodes certain aspects of the spatial temporal structure of the sequence that it was trained on. And so what you can tell by looking at the difference between the red and the blue lines is that the response to the exact same visual stimulus being presented depends on whether it's presented with the spatial temporal structure the mouse was expecting, or if it is presented with a different structure, same images again, but a different temporal structure that the mouse wasn't expecting. Okay, so that's the basic idea that we're following up on. It turns out that there's a lot of really interesting sort of contextual things that change the way visual cortex responds. This happens at different time scales. So this is an example at the bottom of some data where we're showing, again, a sequence of images. The images are just kind of these random blobs, and they are shown in this ABCD or AECD, where E is sort of a new novel element. But the thing that's interesting about this is not happening over days. This is happening just within sessions. So you just start showing it ABCD, ABCD, ABCD. And then every 10th trial, you put in this unexpected response, and you see that obviously you get a different response when the unexpected stimulus comes on. But you also see this sort of wake of activity that changes the response to the expected stimulus that happens later. So very quickly, you just start putting patterns of activity into the brain, and it starts differentiating between expected patterns of activity or expected inputs and unexpected inputs. And this can happen long or over multiple days, or it can happen very rapidly. So this is jumping over a lot of different work, sort of in very brief summary, but this sort of effect that we see that I just described, where you start showing it patterns of information, you do it very rapidly. This might show not only an indication, or might encode not only an indication of what the temporal expectation of the circuit is based on its experience, but also something about the probability. And I say that because if you have conditional sequences where the exact same images change the relationship to each other based on context that is probabilistic, or context that is sort of conditional on a longer component of the sequence, you can see differentiation in the response that seems to scale with the probability of those events occurring. In addition, in layer 4, you can see that the multi-day learning of sequence stuff is actually building these kind of generative predictive representations, and that if you don't, or if you modify the stimulus paradigm so you don't show a stimulus that's expected, you can see the cortex activate at the exact time that it was expecting the thing to happen, but it didn't actually occur. So this data here, I don't have time to go through the exact details of this, but this is basically showing in an animal which has been exposed to this sequence for multiple days, that if you don't show one of the elements and you just keep the element on longer than it should have been, you get an activation of the network that differentiates, or that kind of anticipates when the element would have been shown, which requires obviously some sort of temporal learning to occur in the circuit as well. And the other component of the lab that we're working on is trying to understand how the plasticity rules, or what are the plasticity rules that create these representations. And so we've been studying this mechanistically, and we know that the acetylcholine system is very important for this to happen, particularly muscarinic acetylcholine receptors, and particularly the M2 receptors. And what we're doing right now is working with Anna DeVore's group and doing some imaging of acetylcholine activity. Traditionally, it's been difficult experimentally to image or to record in vivo what the acetylcholine system is actually doing. Now we're using some fluorescent grab sensors to do that and finding some really interesting things. And so just to leave you guys with sort of hot off the press data. So what you're seeing here, this blob of activity is a wave of activity spreading across the visual cortex as a bar is moving in front of the mouse's visual field, coming in from the right hemisphere and moving into the binocular region. So this is the binocular region, and when it gets there, you can see it activates on both sides of the cortex. This is exactly what you'd expect to see if you were looking at calcium activity, but this is not calcium activity. This is acetylcholine signaling happening in real time in these circuits, and it contains this unexpected degree of retinotopy that we weren't expecting to see. And so we're trying to understand the relationship between the acetylcholine signaling, those muscarinic receptors, and the plasticity that we see that encodes the information.